In this video, we're going to talk about normal distributions and the 68, 95, 99.7 rule. So what is a normal distribution? Well, it's described by a symmetric, single-peaked, bell-shaped density curve, which we know about, called a normal curve. Any normal distribution, or normal curve, is completely specified by two numbers. Its mean, mu, a little cat symbol, as I refer to it. So we've got our mean right here, smack dab in the middle, right? Symmetric, single-peaked, bell-shaped density curve. Same deal over here. We've got mu, it's just a little bit taller. And it is also specified by its standard deviation. So the standard deviation this way, standard deviation that way, same deal. That little whoop. I have too much fun with that. That is our sigma. So some more, or the same details in list form. So let's talk about the shape, the center, and the variability in terms of the statistics words that we know. So we know that the shape is symmetric, single-peaked, and bell-shaped. So that bell shape is really what gives it away, at least in my opinion. So the center, again, is the midpoint, and that is our mean, that little mu, lowercase mu. And it's the midpoint of a symmetric density curve and is the same as the median. So mean and median are in the same exact place. So variability, the standard deviation, that little beep, sorry, that sigma is the measure of the variability or the width of a normal distribution. So here's an example of a normal distribution, normal density curve right here. So this is modeled by a histogram of the Iowa Test of Basic Skills vocabulary scores for all 7th grade students in Gary, Indiana. Fun fact, I took the Iowa test scores and I am not from Iowa, nor am I from Indiana. Yeah, super fun. And then over here, if we were to draw that bell curve over it, that's the normal density curve that shows the overall shape of the distribution. So note that it has a single peak, it's symmetric, it's got that bell curve there. Normal distribution, if I've ever seen one. So if we were to find the mean for this data, it's actually 6.84, so smack dab in the middle of our bell curve here. And our standard deviation is about 1.55 on either side. So that means that the average kid in Gary, Indiana, at least whatever year this was scoring at least vocabulary score almost at the 7th grade level. That's what that 6.84 means. It's really close to the 7th grade level. So now let's practice sketching a normal distribution. This example is called Stop the Car. I'm sure you've screamed that at one point in your life. So the problem says, many studies on automobile safety suggest that when drivers make emergency stops, the stopping distance follow an approximate normal distribution. That's cool. Suppose that for one model of a car traveling precisely 62 miles an hour under typical conditions on dry pavement, that the mean stopping distance, mean, our little mu, is 155 feet with a standard deviation of about 3 feet. So let's sketch the normal curve that approximates the distribution of stopping distance. So let's label the mean and the points that are 1, 2, 3 standard deviations from that mean. All right, so here's what we know. We know that the mean, the smack dab center point, is going to be at 155 feet. So I've drawn my horizontal line here, my axis, and I've labeled it as stopping distance in feet. So we also know that our standard deviation is 3 feet. Standard deviation happens to the left and to the right. So we need to do 3 of those, 3 to the left and 3 to the right. And they're each 3 feet in distance. So let's figure that out. So here's what I do. I add and subtract 3 from our original middle point. That's 155 plus and minus 3. So that's 158 and 152 on the left. And then for the second one thing you could do is you could take away 3 from these two numbers and keep going. Or you could multiply 2 times 3, right, which is 6, and add and subtract that from your original number. Both will do the trick. So that's 161 and 149 right here and right here. And then the third standard deviation out is going to be that 3 times 3 plus and minus to that 155. So that's all the way out here at 164 and all the way over here at 146. Now, there's no curve. We need the curve. Let's draw it. Or let's try. Y'all, I tried. I swear I was not shaking when I was doing this, but I got a new pen and, so we start down here. It's really, really slim. It comes up to a really sharp peak, comes back down and mirrors it over here. Here's what it really should look like. I'm so sorry. But you get the idea, right? Cool. So what you may have started to notice is that a large amount of data points fall within 3 standard deviations of the mean, at least in a normal distribution. Well, that rule, it is a rule, has a name. It's called the 68, 95, 99.7 rule. I know, it's catchy, it rolls right off the tongue. So essentially what that says is a normal distribution with a mean, mu, and standard deviation, sigma, that approximately 68% of values fall within 1 standard deviation of the mean. So from this -1 to 1 here, if we were labeling it that way in terms of standard deviations, approximately 95% of values fall within 2 standard deviations of the mean. So from here to here, and approximately almost 100%, but not quite, 99.7% of the observations will fall within 3 standard deviations of the mean. Of course, it's known as the 68, 95, 99.7 rule. Also, note that this rule only applies to normal distributions. I know. Can't have it all the time. So let's take that example we've been working with, the stop the car one, where you're driving 62 miles an hour under typical conditions. I drew that hideous purple bell curve. Don't worry, we'll use this one. Let's find 2 things. Let's find about what % of cars of this model would take more than 158 feet to make an emergency stop. And let's say a car of this model takes 158 feet to make an emergency stop, would be at about what percentile of the distribution? So let's do 2 things with this curve. Finding out about 158 feet. So let's put everything together that we know in order to solve these problems. First up, we've got our curve here. We've got 155, our average smack dab in the middle. Our standard deviation is 3 feet on either side. So our first standard deviation out represents 68% of our data points. 2 standard deviations out altogether represent 95% of our data values. And then 3 standard deviations out altogether represent 99.7% of our data values. So if we find 158 feet, we can then figure out these percentages and figure out what percent takes more than 158 feet to stop. Let's start with the notion that this entire curve represents roughly 100%. I know it's not exact, but we're going to go with 100%. If we remove this green chunk here in the middle, so 1 standard deviation to the left and 1 to the right of the mean, that gives me 100 minus 68 is 32. So everything else is worth 32% or represents 32% of our data. So 2 standard deviations over here, 2 standard deviations over here, 32%. I only need this one, that is 158 and more. So I cut it in half because they are equal. And 32 divided by 2 is 16%. So that answers our question. About 16% of cars in this model would take more than 158 feet to make an emergency stop. And the follow-up question to that says that a car of this model that takes 158 feet to make an emergency stop would be at what percentile of the distribution? So if 16% of the cars in this data distribution take at least 158 feet to stop, what percentile would that be? Meaning, what percent of cars took less? So what's the percent over here? That's an easy subtraction problem. So that's going to be 100 minus 16, which gives us 84. So that means at this point, a car that takes 158 feet to stop, to make an emergency stop, is at the 84th percentile. One last thing that I want to talk about in this video is something called standard normal distribution. So what is that? That's a normal distribution, right? Our bell curve, that's symmetric, it looks beautiful. And we say that the mean, so that number that is at its highest peak, smack dab in the middle, that mean is 0, and our standard deviation is 1. Now, you might think, wow, that's a perfect data set, but we can actually take any data set that would be a normal distribution already and turn it into this standard normal distribution. How do we do that? Z-scores. So if you remember back to when we talked about z-scores, that equation was we take whatever value it was, because z-score was about an individual data point. So we would take that value, subtract the mean, divide the standard deviation. There's its z-score. We talked about percentiles, all that good stuff. So if I took those vocab test scores from Gary, Indiana, and that beautiful, lovely normal curve, and we took all of these values that were down here on this axis. So if we took 2 and 3, etc., and we took all of their z-scores, we transformed that into the z-score, depending on the data with its mean and standard deviation, you would get these numbers over here. So this 2.19 transcribes to -3, and our 6.84 turns into 0. That is our mean. Standard deviation ends up being just 1. So that is an example of turning your normal curve into a standard normal distribution curve. All right, that's going to do it for this video. Thanks for watching.